the equilibrium in phases which are present in a system, and we looked at the Gibbs phase rule, saw the application of the Gibbs phase rule to one component system, that of iron. Today we shall move further and look at system of two components. There are systems with 3 components, 4 components. We shall not go to that. We shall restrict ourselves to 2 component systems. Most of the laws we shall be able to understand with that. In a 2 component system, it's called a binary diagram. In a binary diagram, I have component equal to 2. The variables going to be composition variables and the 2 thermodynamic variables, pressure and temperature. Now to represent these variables on a 2-dimensional diagram, that's on a plane of paper or the blackboard, so what do we do? There are 2 components, composition normally shown by a finite axis with 100% one component here and 100% of the second component there. In between we have the variation of the amount of B going from 0 at 100% A to 100% in B. This is a finite axis. Now I have a composition variable for every phase. That's how you count it, P into C minus 1. Composition of the phase 1 need not be same as composition of the phase 2, need not be same as composition of the phase 3. What was the situation in a unary component? In a unary diagram, we had all phases having the same composition, same component, right? So if there are more than one phases, do I need more axes than these? Instead of one axis, do I have to use 2 axes? There are 2 phases. If there are 3 phases, do I have to use the 3 axes? No. I can do with 1 axis alone. When one phase is in equilibrium, second phase will not be there. Equilibrium has been defined, where the free energy is at its minimum. System would stay in that state where the free energy is at its minimum. If phase 1 is present from 0% B to 100% B, this I have written W oblique 0, W percent is weight percent. Normally engineers work with making alloys, measure 100 grams of A, 50 grams of B, mix them, find out what is the proportion. So we call it weight percent. When we do, the researchers are working, they like to work with 100 atoms of A and 50 atoms of B, so they put atomic percent, they write A oblique O. It's possible to convert weight percent to atomic percent, but mostly my diagrams will be with weight percent. Now let's say there are more than one phase present in the system, and let's say at the given temperature and given pressure, whatever that value may be, phase 1 exists from 0% B to 30% B. Let's call that phase alpha. And the beta phase, the second phase, exists from 80% B to 100% B. Where 0% to 30% alpha is existing, beta cannot exist because that's the equilibrium. Where beta exists in equilibrium, alpha cannot exist. Maybe in between 30 and 80, both of them exist. So it is possible for me to represent same axis at a given temperature and pressure. So one axis can do my work, compression axis, and normally the convention is you have alphabetically the components are written. A here, B there. Let's say for example, silver and copper. Silver you write AG, that will be on the left, copper CU will be on the right. Or you write, let us say, copper nickel diagram. Copper CU start is here and nickel Ni is there. So alphabetically they come in that order, usually. Then you have the thermodynamic variables pressure and temperature. Pressure can be 0 when perfect vacuum, it can go to infinite. So it is semi-infinite axis. While compression was a finite axis, pressure is a semi-infinite axis like I showed in the unit diagram. And temperature is also a semi-infinite axis, 0 Kelvin, so it can go to infinite. So I have three axes, one is finite, other two are semi-infinite. I must have a three-dimensional diagram for the three axes. To represent this on a plane like that of a paper or the blackboard or the screen, it's not convenient. So what we do is, we take a section of this three-phase diagram, or three-dimensional diagram. The diagram is three-dimensional, but we take a section of it. We take a section either at a constant pressure or we take a section at a constant temperature. It becomes a two-dimensional figure. Right? The one which is taken at a constant pressure is called isobaric diagram. The one which is taken at a constant temperature is called an isothermal diagram. Okay? That's what we do. We fix one variable, and the most comfortable variable is one of the thermodynamic variables. Either pressure or temperature. So I shall be left with one semi-infinite axis and one finite axis, which should become a very comfortable diagram to look at. Most of the material systems engineers are working are at 1 atmosphere, except when you are talking about some reactions taking place in the reactor vessel at a particular pressure only. Most of the times we are working at 1 atmospheric pressure. Temperatures could be varying. Okay? So we shall look at the diagrams at constant pressure, isobaric diagrams. Okay? Constant pressure becomes isobaric diagram. So, I have fixed the pressure at 1 atmosphere. In other words, we can also say that I have fixed 1 degree of, or I have exercised 1 degree of freedom in the system by choosing one variable, that is the pressure, as 1 atmosphere. So I have exercised only 1 degree of freedom. So my modified phase rule for the binary system, which is represented in 2 dimensions, will be, recall your phase rule, this 2 has become 1 now because I have exercised 1. I have exercised 1 degree of freedom. Degree of freedom has become 1 less, so that's become C plus 1. That's 2 was coming for pressure and temperature, I exercised pressure. Right? So it is a modified phase rule. Now in a binary system, C is equal to 2. So F becomes, C plus 1 is 3, so it becomes 3 minus P. Now let's look at here, number of phases, variables, degrees of freedom. If I have only one phase present in the system, how many variables shall I have? One. Number of variables in the system are pressure and temperature and compression variables. So if it is one phase, there will be one compression variable. And out of the pressure and temperature, I have already exercised pressure as 1 atmosphere, so I am left with 2 variables. And the 2 variables I am left with are composition and temperature. So how many degrees of freedom do I have? 2. 3 minus 1 is 2. You can change both composition as well as temperature within the boundaries of the system or boundaries of the phase diagram. Alpha phase or the single phase, whatever is there, shall remain in equilibrium. If I have 2 phases present in the system, how many variables do I have? 3. Out of which 2 will be compression variables and 1 will be the temperature. Okay? And degrees of freedom I have is 1. Degrees of freedom I have is 1. That is, out of the 3 variables in the system, compression of the phase 1, compression of the phase 2, and the temperature, I can exercise now to fix any one of them if I want to see the equilibrium between phase 1 and phase 2. If I fix the temperature, compression of phase 1 and the compression of phase 2 will be fixed. If I fix the compression of phase 1, then the temperature and the compression of phase 2 will get fixed. That's the meaning of it. I shall show you all this with the system. Okay. Then if I have 3 phases present in the system, variables I have 4. Compression of phase 1, 2 and 3. 3 variables, temperature the 4th, and I have 0 degrees of freedom. So all the 4 will be fixed. Compression of phase 1, 2, 3 and the temperature. Everything will be fixed. There's such a thing is like a triple point in the unary system. We call such situations invariant. No variable can be varied. Okay. Now, before we start making the diagram, we use the convention for writing liquids. We use capital L. For writing solids, we use alpha, beta, gamma, Greek alphabets. This is what we use. And we are not looking at the system where we have gases present there. So we are looking at liquids and solids. The solid melts, I get liquid. Then I define another thing in the diagram, the tie line. The tie line is drawn in the diagram. Now I have whatever variables, compression and temperature. Compression axis is 1, which is finite, temperature axis is semi-infinite. And we draw a constant temperature line in 2-phase region. That's important. This is not drawn in a single phase region. In that case, once we do that, the ends of the tie line are ending at the ends of the 2-phase region, and they give these ends the compression of 2 phases which are in equilibrium. this two-phase region, alpha and liquid. In this two-phase region, this is, let us say, is the constant temperature line. And let us say here is the alpha phase region, here is the liquid phase region. I'm just saying that, okay. So this gives me the composition of the alpha phase, this gives me the composition of the liquid phase. Is it clear? Right. So when you look at the actual diagram, this is just hypothetical thing which I showed you. We shall now look at one of the simplest of the binary diagrams. It's called an isomorphous system. Isomorphous means the two components dissolve in all proportions in the solid state as well as they do so in the liquid state. We shall be seeing the diagram where most of the components dissolve in all proportions in the liquid state. But they may do so in solid state, they may not do so in solid state. If they do so, if they dissolve in each other in all proportions, I call it an isomorphous system. Iso means same, morphology is the same. In the solid state, it is all the way FCC, it is FCC from 0% of B to 100% of B. If it is HCP from 0% of B to 100% of B, it is HCP. That's morphology, and this is why it's called an isomorphous system. Some of the examples of the isomorphous systems are copper-nickel diagram is one, gold-copper diagram is another, silicon-germanium diagram, Al2O3Cr2O3 diagram, so the one. These are the ones which are providing the gemstones. Okay, ruby comes from there. Alright, here let me show you a diagram. This is the composition axis. Weight percent of, let us say, nickel. This is 100% nickel, and this is 100% copper. That's the temperature. And here is the melting point of copper, which is 1083 degrees centigrade. This is the melting point of nickel, 1453 degrees centigrade. And this is the single phase field liquid, this is the single phase field alpha, solid phase we call alpha, and in between I have the two phase region here. In this diagram, I have only two lines. One is the line, this one, which I call liquidus. There is other line which is here, we call it solidus. And as I had said, this is 0% nickel at this end, 100% nickel at that end. What is liquidus? What is solidus? Let's define that. Liquidus is the locus of temperature points above which the system exists only as liquid. And I have not defined what exists below that. Above that temperature. Yes? Above this temperature, it all exists as liquid. What exists below this temperature, I am not defining. Similarly, solidus is defined as the locus of temperature points. Below that temperature, it is always solid. What is above that temperature is still not defined. So, below this line, it is all solid, alpha phase field. So that's the solidus. Between the liquidus and solidus, I have the two-phase field, which contains liquid and solid. Alright? Yes, please. Yes. Yes. 1. Please let me see how to read the diagram. I have not told you how to read the diagram. I have to show you 3 variables first. Right? I have given you a table. I have to show you 3 variables. How do you read that? But I have already given the hint. I have to explain that. Let us all first of all read the one-phase region. In one-phase region, the number of variables we have are 2. One is the composition, another one is the temperature. 2 into C minus 1, 1 into 1. 2 minus 1 is 1. So that's only one composition variable, plus 1 temperature. Degrees of freedom, 2. Both the variables composition and temperature within the boundaries of the system you can change. The boundaries are here. This solidus and this temperature line, this composition line and that temperature. They are the boundaries. Within this, let us say I am at this position, at this composition. I change from here the composition to this value, still in alpha phase. I change the temperature also, let us say, to this value. I am still in alpha phase. Well, you can go from here, both changing composition and temperature are still in alpha phase. Both the variables are the degrees of freedom, as long as you are within the bounds of the area. Same is true about the liquid region. Alright? So that's how the phase rule is to be read here. Phase rule, which is again right. Alright, let's look at the two-phase region now. This is the two-phase region here. To read the two-phase region, we draw a tie line. So the equilibrium is seen by the tie line. This is liquidus and I have drawn the line down to the composition axis. That gives me the composition of the liquid phase. This is the solidus. I draw the line parallel to the temperature axis on the composition axis. This gives me the composition of the alpha phase. And when I read on the temperature axis, I read this is the temperature. Let's call it T star. At temperature T star, in this region the two phases which are in equilibrium have the composition C liquid for the liquid composition phase, C alpha for the solid phase. They are in equilibrium. These are how we read the 3 variables. Right? So in two-phase region, the variables I have are 3 and degrees of freedom I have is 1. But you can go back three variables, the temperature T star, composed of the liquid phase Cl, composed of the alpha phase C alpha, you fix any one. Which one should be fixed? That is a T star, temperature. At that temperature, this is the only tie line in this region. And this is the end of the tie line on the liquidus. This is the composition of liquid phase Cl. This is the end of the tie line on the solidus, that gives me the composition of the alpha phase solid phase. So Cl and C alpha get fixed automatically once I fix the temperature. Let us say you decide to fix, you want to find out what is the composition of the liquid and what is the temperature at which solid of C alpha composition is in equilibrium. So find out C alpha, draw a line parallel temperature axis up to the solidus, from there draw a tie line. That gives you the temperature at which this is in equilibrium, and the end of the tie line from the liquidus gives the composition of the liquid phase which is in equilibrium. That's how this phase rule is looked at in this diagram. And phase rule says there's only 1 degree of freedom. I can change the composition and the temperature simultaneously. Yes. Or what? Then the composition of what I'm changing. This question is this. Composition of the alpha phase I can change along the solidus only. Composition of the liquid phase I can change along the liquidus. I cannot change the composition from this to this like that for the liquid. No. I don't have a liquid here. Do I have liquid there? Liquid is only above this liquidus.
So what I'm saying is within the liquidus alpha region, you can change for a particular point within the area.
Changing of what? I have two phases. I'm changing composition of what? I'm changing composition of what? One phase or both the phases? What is it you are asking? Now when you have two phases, you have to worry about the composition of each one of them. Composition of the one varies in this region along this line. That's for the liquid. Composition of the solid varies along this line. And then two of them have to be in equilibrium. Okay? Two of them are in equilibrium at a constant temperature only. This one is in equilibrium with that at this temperature. Similarly, at another temperature also they can be in equilibrium. I have changed the temperature. But what is in equilibrium is this composition of the alpha phase and that composition of the liquid phase, which are different from these. It is not the same equilibrium. It's a different equilibrium. At some other temperature, let's say lower temperature here, this is the solid which is in equilibrium with this liquid and the temperature is different.
It means that two phases are in equilibrium with a specific concentration in both the...
Obviously, because I have only 1 degree of freedom. I am looking at a particular temperature. Then the two phases have the two compositions which are fixed. Composition of liquid phase as well as the solid phase, they are all fixed. I can't change it at this temperature. At equilibrium. Otherwise they are not in equilibrium. If
This is the area between
yeah, they are in equilibrium. Is this clear? Right. In this diagram, I do not have three phases in equilibrium. When I have an isomorphous system, in the isomorphous system, I do not have three phases coexisting together. Three phases can coexist together in systems which do not show complete solubility in the solid state. We shall come and talk about that when we reach there. Now before I proceed further, I take, let us say, in this system, an alloy which I made by adding 50 grams of copper and 50 grams of nickel. So composition is 50-50. I call this composition C0. I take 50 grams of copper, 50 grams of nickel, put them in a crucible, take it in a furnace, say up to about 1400 degrees centigrade, melt it. Stir it completely, make a good melt, homogeneous melt. Right, now it's asking what shall be the microstructure of this alloy when it is cooled at different temperatures from the melting point. Let's say I am at this temperature, which is in the molten state, the liquid state. Call this temperature T1. It is above liquidus. It shall be all liquid. There will be nothing else. In the crucible I shall see all liquid, because I am in a phase field where there is only single phase, which is liquid. This situation shall remain till I reach the temperature of liquidus. When I come below liquidus, solid will begin to come in equilibrium with it, and that's how solid will start to form. In other words, for this alloy, solidification begins below liquidus, and that solidification shall continue up to solidus. Let's look at what happens in this temperature range. The temperature between liquidus and solidus let's say some temperature here. This is the composition of the liquid phase, which is different from C0, and this is the composition of the solid phase, which is also different from C0. C0, Cl and C alpha. Those are in equilibrium. Right? So I have a liquid in which some particles of alpha phase are there. With composition C alpha. These are the alpha phase particles.
This is unique. For this temperature, this C alpha and the liquid.
No, this is equilibrium composition is that only, and rest is all liquid. That's how the microstructure will look like. The system will look like. Look at the crucible. This is how it will look like. Some particles of solid floating with the composition here, and the liquid with the composition there. And this situation shall go on till I cool reach up to the solidus. But the amount of solid will keep on increasing. Amount of solid was 0 just at the liquidus, and this amount of solid shall keep on increasing as I go down, and it shall become all solid by the time I reach solidus. So now I am below solidus. Once I reach here, below any other temperature, let us say this temperature, this will be all solid. Now all the particles which had formed, they start impinging on each other after a while, and I form a polycrystalline solid like this. Usually we get polycrystalline solid. Each one is a grain of alpha phase, and we have the grain boundaries in between. That is what happened now below solidus. Right? Yes, this has all become already 100% solid. Now below this it shall all remain 100% solid, because that's the definition of solidus. means it is all 100% solid. But it is polycrystalline. It's not a single crystal. Usually the way we grow it, we solidify it, automatically it will form a polycrystalline one. Because the nucleation at liquidus begins at more number of places than one. And then they each grow in size and some more nucleate as we cool. And that's how the amount of solid keeps on increasing. So in this alloy, the solidification is not taking place at single temperature. It is not congruent melting. Like at the pure copper melts at 1083, pure nickel melts at 1453, and this is congruent melting. At a single temperature it melts. But in here it melts solidifies over a range of temperature, starting from liquidus up to the solidus. Okay. So you see, you have an alloy of composition C0, but in a two-phase region, I have two separate phases, each one of a different composition. But the total composition of the alloy combining alpha and beta together, liquid and alpha together, is only C0. Mass has to be balanced. Mass cannot remain unbalanced, Whatever you started with. You started with 50 grams of copper, 50 grams of nickel. That is getting divided into two phases, liquid and alpha, but different composition, in different proportions. And that goes on during solidification.
Also the composition is remains same.
Composition of the overall alloy, which is the combination of alpha and liquid together. That should remain the same.
Even if all the liquid has been converted to alpha, in that alpha
All the liquid is 50 gram nickel, 50 gram, all the solid, 50 gram nickel, 50 gram copper. But alpha and beta, when two are existing together, it will be 50-50. One will have less of copper, other will have more of copper. Is it clear? Right. That's what I'll show here now. Series of alloys at a constant temperature, let us say 1300 degrees centigrade. Let's say this is 1300 degrees centigrade. This is liquid here, alpha here, liquid plus alpha there. That's the composition of the liquid phase, and that's the composition of the solid phase. Let us take one alloy which has a composition Cl at this temperature. Alloy which has a composition Cl, what shall it have? What shall it will show me? The composition of the alloy itself is Cl. At this temperature, what will it show? All liquid, 100% liquid it will show.
even at this temperature, alpha can also exist in equilibrium. Can alpha exist?
I'll come to that. I'm just at the liquidus. What shall be the amount of the solid? Will come to that. So this is going to be all liquid. Well, if I have a composition of the alloy C1, it shall have liquid and solid both. The liquid of this composition and solid shall have that composition. Amount of solid would be small, probably not very large. Alpha phase is present here, and rest is all liquid. That is composition C1, that's composition Cl. Let's take another composition here, C2, slightly still to the right, but less than Cl, alpha. solid probably. Than what we had in the earlier case, and we shall have less liquid. This is compression C2. But the fourth compression, let us take, is compression C alpha. It is all solid. There are alpha grains. So here I have 100% liquid, here I have 100% solid. In between, the amount of the two phases is varying, but the compression of the two phases is the same. Liquid compression Cl. Here the liquid compression Cl, alpha compression C alpha. Liquid compression Cl, alpha compression C alpha. Alpha compression C alpha. Compressions are not varying as long as the temperature has been maintained at 1300 degrees centigrade. Temperature is constant, fixed. Is that clear? Right.
So in C1, whatever amount of C alpha solid has appeared, it has appeared with the composition
C alpha only, yes. What's equilibrium means that? I'm talking about the equilibrium diagram. If it is not in equilibrium, non-equilibrium could be anything. But if it is in equilibrium, that's what it is. Now I have introduced already saying that at this alloy, that's a two-phase region here. This temperature is a tie line. Let's say I take an alloy compression C0. The compression of the liquid is Cl and compression of the solid is C alpha. At this temperature, this is my C0 alloy. I consider to find out the relative amounts. I showed you just now how the compression of the alloy changes, the amount of solids is changing. But I am going to give you now what are the relative proportion of the two phases. It can be given. It's of course nothing but the mass balance. I suggest there's a problem in the book as well as I suggest that you work it out. Balance the mass in liquid phase and the alpha phase and put it equal to the total mass which is there in the alloy. We'll see that the tie line acts as a lever of the first kind with the overall compression of the alloy as the fulcrum, mass of the liquid phase hanging at the liquidus and mass of the solid phase hanging at the sand of the solidus, and tie line has to be maintained horizontal. So the mass of the solid phase which hangs here and the mass of the liquid phase which hangs here they have to be in proportion to the arm of the lever which is opposite. For the liquid it should be this, and for the solid it should be that, so that the lever is maintained horizontal. So you can see the mass fraction of the alpha phase, I call it M alpha is equal to the proportion of the alpha phase is here, so it is the opposite arm of the lever is this, so that is C0 minus C liquid divided by C alpha minus C liquid. This arm of the lever divided by the total arm of the lever, or total length of the lever. That's the denominator. Similarly, the mass fraction of the liquid phase is proportional to this opposite arm will be C alpha minus minus C0 divided by C alpha minus C liquid. That's what we call the lever rule. And this can always be worked out. Now I shall answer your question. What is the amount of solid when I am at the liquidus here? The fulcrum is right at the CL. What shall be the amount of solid? 0. That's why I showed a complete liquid there. Amount of the liquid is 0, a solid is 0 here, and amount of the liquid on the same count will be 0 there. That's why I said is solid phase hanging here, is a liquid phase hanging there. Is that clear? Right. Now there is, I have told you about the phase rule, I have told you about the tau line and tau line rule, I told you about the lever rule. I told you about another rule, what is called the 1-to-1 rule. 1-to-1 rule, in the phase diagram, you draw any constant temperature line. Let's say this is A, B, percentage of B there, temperature here. So draw a constant temperature line here. Along this line, I have phases arranged 1, 2, 1, 2, 1, 2 like that. That's 1-to-1 rule. That means every two-phase region on either side has a single phase region. And those two single phases are those which are present in that two-phase region. That is, if you look at here, from this temperature axis up to this liquidus, I have liquid phase present here. That is 1. Between this liquidus and this solidus, I have two phases present, liquid and solid. And from this solidus up to this temperature axis, I have only one phase present. That's 1-to-1. Now, a one phase region can be very narrow, it can be very wide. See, it can be narrow, it can be so narrow that in this axis which I am showing, it may just look like one single line. It's possible. It can be a little wider, which can show it on the diagram. Depends what percentage range you are talking about. Here I show the one phase region is this much as compared to that. If I was at a still higher temperature, here, what is the one phase region? Very narrow. So that's what is. I said one phase region can be narrow. It can be as narrow that I can show it just as a point or a line in the diagram. Because after all, 0% to 100% has to come within this range. A to B, 0% to 100% has to come. Right? Okay. So that's what is a 1-to-1 rule. Alright, next we try to look at the other kind of diagrams which show partial solubility in the solid state while they show complete solubility in the liquid state. Some of these diagrams I mentioned, I am not mentioning all such diagrams. Eutectic diagram, eutectoid diagrams, peritectic diagrams, and peritectoid diagrams. We shall see them one by one. So first start with the eutectic diagram. Let's say AB here, weight percent tin there, and here is the temperature axis. The melting point of lead, field, that's the beta phase field. Here are liquid and alpha phase field, liquid and beta phase field, alpha and beta phase field. Here we have boundaries which are defined liquidus. This is liquidus 1 from the melting point of lead, which is 327 degrees centigrade, goes up to this temperature, which is 183 degrees centigrade, and this composition up to which it goes is 62% of tin. And the second liquidus is here, which starts at the melting point of tin, which is 232 degrees centigrade, and goes again to 183 at 62%. Similarly, I have this solidus line here. This is one solidus line, and that's the second solidus line here. Besides that, I have this boundary and now this boundary, plus I have this line. These are the additional things other than the liquidus and solidus which I defined earlier. Solidus, below which it is all solid, liquidus, above which it is all liquid. But what is this line? This is the solubility limit. It gives how much tin can be dissolved in lead at a given temperature, and then it becomes supersaturated. So solubility of tin in lead is given by this line at different temperature. It's called solvus. You can call it solvus 1. Similarly, this one can be called solvus 2. That is how much of lead can go in tin. That's solubility limit of lead in tin. Alright, that's called a solvus line. Well, in complex diagrams we shall see more of these. And this temperature line, constant temperature line, 103 degrees centigrade, we shall see in the next class.